Alright, listen up. Page 537. And we're going to talk about geometric mean and similarity. Okay, this first key concept to get into your notes. The geometric mean of two positive numbers is the square root of their product. The geometric mean of two positive numbers is the square root of their product. The geometric mean, or let's just do this. Come on, eraser. Come on, baby. Come on. Come on. She's a-coming. There we go. If you're asked to find the geometric mean and you're given the numbers 5 and 45. Alright, the geometric mean of 5 and 45, you can say the geometric mean is equal to the square root of 5 times 45. So it's just a calculator problem. You take 5 times 45 equals, and you push the square root button. So the geometric mean of these two numbers is 15. If you have to find the geometric mean of 12 and 15, alright, the geometric mean would be equal to the square root of 12 times 15. $13.4. Everybody alright with that? Alright, so look at the top of page 538. Theorem 8.1. If the altitude is drawn to the hypotenuse of a right triangle, then the two triangles formed are similar to the original and to each other. If the altitude is drawn to the hypotenuse of a right triangle, then the two triangles formed are similar to the original triangle and to each other. What that means is if you've got a right triangle, and if this is triangle ABC, the altitude of a triangle goes from a vertex to an opposite side, and it intersects it at 90 degrees. So when you're talking about the altitude is drawn to the hypotenuse, the altitude would have to come out of this right angle and go to the hypotenuse. And here it is, and we'll call that point D. Now, do you see how that altitude forms two more triangles? The smaller one on the left and the bigger one on the right. What this rule says is that the two new triangles are similar to the original triangle ABC and to each other. So today you'll be writing some similarity statements that address that. So a similarity statement that relates these triangles would be, we could say that triangle ABC is similar to triangle. Now, ABC went short leg, long leg, hypotenuse. Agreed? That was the order of the vertices. A to B is the short leg, B to C was the long leg, hypotenuse is what was left. That pattern is the same pattern you will use when you describe the other two triangles. So we went short, long, hypotenuse. So in this next triangle, we're got to go short, long, hypotenuse. So what would that triangle be labeled? ADB, good. And that triangle is going to be similar to, we're going to go short, long, hypotenuse again. So here's this third triangle. Here's the short leg. Here's the long leg. And here's the hypotenuse. So that third triangle will be labeled BDC. Agreed? Does everybody see that? It looks like in most of the problems you'll be able to go short leg, long leg, hypotenuse. Short leg, long leg, hypotenuse. But if for some reason the triangles look very similar in size and it's hard to tell the difference between the short leg and the long leg, just choose to go either clockwise or counterclockwise. Alright? And then just stay consistent throughout your description of the triangles. Always verify, okay? One way to verify your answer here is to always make sure that your hypotenuses are in the same location in your description. So in the big triangle, your hypotenuse was AC, wasn't it? Alright, first and last. So in this middle triangle, the green one, I should have used yellow there. First and last was hypotenuse. In the green triangle, the hypotenuse was this AB, first and last. And in the blue triangle, the hypotenuse was this side BC, alright, first and last. Okay, so that's a quick check to make sure that your description is in the correct order. Top of page 539. Right angle geometric mean theorems. The altitude drawn to the hypotenuse of a right triangle separates the hypotenuse into two segments. The length of this altitude is the geometric mean of the lengths of the segments. The altitude. The length of the altitude. Is the geometric mean of the two segments. Alright, and then let's get this rule written down as well. Right below it. The altitude drawn to the hypotenuse of a right triangle separates the hypotenuse into two segments. Okay, we'll just write it down again. The altitude. Drawn to the hypotenuse of a right triangle separates the hypotenuse into two segments. The length of a leg of this triangle is the geometric mean between the length of the hypotenuse and the segment of the hypotenuse adjacent to that leg. So let me slide this over. If you've got this triangle for this first rule, if you've got a right triangle, ABC, altitude drawn to the hypotenuse, this altitude, CD, created two segments in the hypotenuse. We'll call the segments X and Y. I'm going to call this altitude right here H. Alright, what that first rule said was that the H is equal to the square root of X times Y. The length of the altitude is equal to the geometric mean of the two pieces or the two segments that it created. Does everybody see that? The length of this yellow piece right here, the altitude, is equal to the geometric mean of this piece and this piece. the two pieces it created in the hypotenuse. You got that? The second rule. Second rule says now you've got an altitude drawn to the hypotenuse again. The altitude drawn to the hypotenuse of a right triangle separates the hypotenuse into two segments. Your two segments now are x and y. The length of a leg of this triangle, that means either side B right here or side A. The length of a leg of this triangle is the geometric mean between the length of the hypotenuse and the segment of the hypotenuse adjacent to that leg. So, this side B right here, side B, little letter B, is going to be equal to the geometric mean of x times c. This side, this yellow side, is equal to the geometric mean of the hypotenuse and the segment adjacent to the side. Alright, hypotenuse and segment adjacent to the side you're trying to find. Which means that side A would be equal to the square root of, alright, you got side A right here. It's going to be equal to the square root of the hypotenuse times the segment adjacent to its side. Alright, so that's going to be c times y, or y times c. And then you just have to do the math. Alright, so 3 different situations today. The altitude drawn to the hypotenuse is equal to the square root of the two segments multiplied. One of the legs of the triangle, this side B right here, is equal to the square root of x times c. This leg of the first right triangle is equal to the square root of this segment y times the length of the hypotenuse. Okay, does that make sense to everybody? Let's do one. Let's look at example 3 right there. We've got this triangle, this right triangle. KLJ. Here's your right angle. Here's your altitude drawn to the hypotenuse. And this is point M. And here's the given information. We've got a 5, a 20, an X, a Y, and a Z. Alright, so the first rule that you got today said that your x is equal to the square root of 5 times 20. Agreed? The length of the altitude is equal to the geometric mean of the two pieces it creates. So your x here is equal to the square root of 100, which equals 10. Your y is equal to the square root of the hypotenuse, which is 25, the hypotenuse times the piece adjacent to it. Here's the piece adjacent to it. Right here. It's next to the side y. So y is equal to the square root of 25 times 5. So y equals the square root of 125. And when you do these today, just round to the nearest tenth. That's 11.2. There's your y. And then your z is going to be equal to the square root of z, side z, is going to be equal to the geometric mean of the hypotenuse and the side adjacent to the leg. So in this case, side z is going to be equal to 25 times 20. So that's going to be the square root of probably 500, which is 22.4. Alright, so there's your x, there's your y, and there's your z. Any questions? Alright, some practice for you today. Page 541. Eight through 23. 8 through 23. And please be sure to check focus for your online assignment.